Hello guys, welcome to the second webinar. Today I'm going to talk about convolutional neural networks. It's like a continuation of the previous webinar where I gave some intuitions about neural networks. So let me share the screen with you. So I will basically give you, I have prepared two presentations. The first is like an overview of CNNs, convolutional neural networks. And the second one is something that I really enjoy, are spreadsheets. So I'm going to implement like the feed forwards for convolutional neural networks in spreadsheets. I hope in this way to show that convolutional, this operation is actually simple. It's not so difficult. All right, so let's start with this first presentation. My goal here is like just to give a overview of CNNs. First, I'll show what we've seen so far, like from the previous video. Then I will show a problem from that implementation and the solution. So we've seen so far from the first webinar this architecture here. So this is an architecture called fully connected neural networks, in which we have the input, the output, and hidden layers. And we have weights that are associated to each one of those inputs. We also have a constant value, a bias that I forgot to put here. We sum all of them, we apply a activation function, and then we go to the hidden layers, where this very same process is repeated here. And actually this connection here is made with all the hidden layers. And I showed that usually you will see architectures of neural networks in this way. This is a simplified way to see, but as I said, you always have to keep in mind that you are going to sum and then apply a activation function for each of them. In another detail, it's that you don't necessarily have only one output. Here, you actually can have multiple outputs as the input. All right, and this architecture is useful to find correlations of features in the input. So, like some examples of features that I gave from the previous webinar was like age, gender, and ticket price. This was the case with the Titanic disaster. So we tried to correlate them in order to give a output. In that case was if the passenger survived or not. However, what if your input is an image? In this scenario, how would you connect an image into this architecture? I have here one more example. For example, I have one handwritten digit. How should I connect in this architecture? So one possible solution would be to turn each pixel into one input value of this neural network. So you're going to cut this into pixels, and for each pixel you have one new input in this architecture to try to correlate with the output. However, there are some problems with this approach. One of them is the complexity. For example, if my image has 24 by 24 pixels, then it means that I would need 780 84 units just in the input layer, and this is going to grow. This is going to grow exponentially. So it would be very complex actually to connect each pixel to convert as one input in the fully connected network. Another problem is that the pixels aren't really features. What do I mean by that? What ideally we want to connect in this architecture are features from this image. Some are like characteristics from this image. Some examples of features from this image are if it has wheel, if it has door, and if it has mirror, for example. So like giving those features, then you can classify if this image is a car or not a car. So ideally, we want something in between that can extract those features for us in order to then classify here and give us an output. And so this is the second problem. And the third problem is that the weights will be sensitive to the position of the image. I have here one example. I forgot to load before, but it's loading now. What do I mean that weights will be sensitive to the image position? So I have here one example in which this image, it's a handwritten digit. It's converted, each one of those pixels is converted here as one possible input. And then here I have weights that are associated with each one of those inputs. However, in this scenario, each weight will be linked to the position of those pixels. And for example, those weights here are going to get specialized on those pixels here. However, the concept of the number one, they will not necessarily will be in those pixels here. So for example, if I still will have a number one, if I had written it here in this corner. So now I don't have, I changed here the position. It's not the very same weights as before. Instead of those weights, now I have those weights. So this is another problem of connecting each one of the pixels as one possible input in my neural network. So we need a better solution. And what's the solution? It's the name of this video. It's the convolutional matrices. That's a better solution. So what do I mean by that? Here we use this concept of kernels. So let's suppose this is my input image, and instead of having one weight for each one of those pixels, instead of this, I will have a kernel, and this kernel will have the weights of my neural network. So in this case, I have a kernel that is 3 by 3. So in other words, I have 9 weights to be learned by the neural network. And those 9 weights, they will go through all the pixels of my input image, and then they are going to generate a new image, which is called feature map. So by using this kernel, the kernel is going to map my input image into a second image. And the goal of applying this kernel kernel is to extract features, a specific feature from this image to be mapped to this second image. How does this happen? So I have here one better illustration. I have as input image a binary matrix. We can suppose that this is a square. The 0 are the white color and 1 could be the black color. So I have a square here. And the operation is quite simple. I have my kernel matrix. And again, this kernel is actually learned by the neural network. I'm giving here some values as example. And we will perform here a element-wise multiplication. So this first element is multiplied by this one. This second element is multiplied by this one. And then we sum all of those values. So by multiplying and then summing, in this case, we'll have the value 2, which is going to be mapped to this feature map. And then we'll go through all other values, and then they are going to be mapped to this feature map image. In this case, I've chosen values here that are actually going to map this image into a edge detection image. So you can see that I have in the middle 0, and around I have values. So you can think as output here the edge of this square. And this is actually the kernels. They actually are already used as image processing methods. So they didn't come with convolutional neural networks. They already existed before. And yeah, they are useful in order to process images, to perform some operations in the images. So for example, if I use those values as a kernel and apply it to this image, then I will have a Gaussian blur in effect in the image. Or I can also have a sharpen effect or a edge detection. So those values are also useful for edge detection. I can either use those values or those values here. Okay, but here I am inputting manually those values. And again, in the neural network, though this kernel is learned automatically, the neural network is going to find out each one of those values is going to be a and weight. So let me give you an illustration of how this process would happen in image. So let's suppose this is my input image, and then I would have a set of weights here as a kernel that would go across all the pixels of this image. So it's basically this is what's going to happen. And then I would have a new image, which would map this image into the features that were depending on the weights that were found out here. I'm giving an example here as this kernel here learned how to extract the edges of the image. But this is something that it's just for illustration. I could have any other image here. And also, in my input image, I can have many kernels going through. I don't need just one. So for example, I will add one more kernel here that will go through all the pixels of the image, and suppose that this second kernel is applying a blur effect in the image. And okay, so we still have the same problem. We have our input image. We have now 2 new images, like with features, but we still have the problem. What's next? How can I connect those 2 images in this architecture that I showed before? So the next step here is a process, a method called max pooling, which is a fancy name for subsampling. So we are basically going to reduce the size of this image, subsample it. And this process is very simple. I have here an example. For example, in this, suppose that this is my input image, and I have a 2 by 2 matrix to subsample. So I basically will have always I will get in those 2 by 2 blocks the maximum value of those blocks. So in this first block, the maximum value is 2. In this second block is 2 as well. Actually, all of those are 2. So this is a method to transform a 4 by 4 matrix, in this case in a 2 by 2, to reduce this matrix into a half. So this is what happened in next after convolutional filters. We subsample it, so we'll have a reduced image that tries to represent the previous image into fewer pixels, into fewer units. And then, after subsampling, we will repeat this process. So we basically, in convolutional neural networks, this is the sequence of events. We first apply convolutional filters and then subsample. Then we apply again convolutional filters, then subsample again. So I'll give you one more example here, like continuing this. So I have convolutional filters, subsampling. Let me repeat this again. So let's suppose that I have again 2 kernels, 2 convolutional filters. And since I have 2 images here, I will apply 2 kernels to 2 images. So I'll have in total 4 images. This is again like illustrations of how they could look like. The goal here is to show that after a while, those images, they are becoming more abstract. And then if I subsample them again, then I'm actually just reducing their size. So after a while, those images, they become more abstract, and each one of them can become more specialized in one type of feature from this input image. And then finally, if you repeat this process many times, and then you have multiple images, and then one last step to connect into this architecture is the flattening process, in which we'll get each one of those pixels, but now of those reduced images, and then turn this into a one-dimensional array. And then this array will be connected into my architecture. So yeah, this is a better solution for extracting features from the image in order to then connect to our classic fully connected layer, which is this one. And now the question, how does it really work? Does it really gives good results? Well, it actually gives. I want to show you this paper. It's a very classic paper from convolutional neural networks, which is called Visualizing and Understanding Convolutional Neural Networks. And there are some images, very good images, that they are showing they used a model that was a deep learning model that was trained with millions of images, and then they learned a way, they are showing in this paper, a way to visualize the kernels of those images. So they're showing here some examples of kernels that the neural network learned by itself in the first layer. So we can see here that in the first layer, you didn't tell the neural network to do this. It learned it automatically to identify some edges in the image. So here are some examples extracted from images of what it learned. So this is like the most basic feature that in the first layer, the neural network learned by itself. Then next, in the second layer, here are some examples of filters or kernels. It's the same thing that it learned automatically. And here are some images that were activated from those kernels. So you can see that in the second layer, now the neural network learned more complex features, such as round shapes or like corners and straight, some patterns. And yeah, here we can see some images that were activated with those. And then finally, as you go deeper and deeper in the layers, the kernels got more specialized. So here in the third kernel, in the third layer, we have kernels that learned how to identify like wheels or grids here, or even human faces. So we can see that the convolutional neural networks, the kernels, they can become very powerful to extract features from the images to later be used for connecting in the fully connected network that I presented in the first webinar. And okay, so yeah, that's the first video. So in short, the CNNs, the convolutions of the network, they are used for extracting features from images, and they are usually combined with max pooling in order to reduce its dimension. And as one of the advantages besides extracting features is that it requires less complexity when compared to connect each one of the pixels to the network. Now you have like like for example 3x3 kernel that is going through all the pixels of an image, so they are actually less complex. And okay, so that's the first video. Before going to the next one, I just want to check if there is any question. Okay, how you choose the values from kernel matrix? Yeah, that's a great question. It's, as I mentioned, this is like the what's really interesting from the convolutional neural networks. They will learn the values of the kernel matrix automatically. This is something that I confused in the past. I thought, oh, I am going to input those values, but no, they are actually learned through gradient descent. So it's basically in the same way that the weights of a fully connected network are learned, the values from the kernel are actually weights in the neural network, and by using gradient descent, by getting their derivative, you can update those values. So at first, those values are random, but then later they are going to become more specialized in specific features they learned automatically how to extract features. Okay, so my goal was just to give a big overview of the convolutions, but now let's dig deeper and implement them. And I find spreadsheets a better tool than Python. Python is like procedural programming language, but spreadsheets are great for like visualizing. You can in real time visualize what's going on. So that's why, like for understanding something, I think they are a great tool. But so I will first visualize, I will first show you a link and then go to the spreadsheet. So first I want to show you guys this link. It's a visual demonstration of neural networks. So this is an online implementation of the MNIST problem using convolutions. So first, I will hide here some layers. So what's going on here? So you basically, I can draw any number here. For example, it's difficult here. Yeah, 6, and then it's going to give my guess, and it's actually guessed wrong, 5, and I actually sampled 5. So let me try again. I will try 7. My first, and it predicted 7 as first guess, and it predicted 4 as second guess. So, and what I have here are the steps, like the convolutions and the downsamplings that I presented before, and then the fully connected layers. So my first layer here, I have my input layer, in which it contains the value that I just drawed. So for example, here was 7. Let me put I'll put 1 here. 1. And then, so as I mentioned before, the first step is to apply convolutions. So here we can see that we have 1, 2, 3, 4, 5, 6 convolutions. So in the very same image, 6 filters were applied to this image, and each one of those filters became specialized in one specific feature of this image. Let me draw a better number. Let me try 4 here, for example. It guessed 9. Let me try again. 4. Okay, yeah, my first guess 4. So we can see here that, for example, this kernel here is more specialized in the right edge of an image, while this kernel here is more specialized in the bottom edge of an image. Then all of those images, they were downsampled, so it's the same image but with a lower dimension. And then the kernels are applied again. So we can see that now they become more abstract, but at the same time they are learning to be more specialized in specific features. And then downsampling again, or max pooling. And finally, those pixels here, they are flattened and then connected to a fully connected network. That's the classical network. And then they have here 2 hidden units, and finally an output here. So finally, the value that was higher here in the sum of activations, in this case, was 4. So this is a very good example. You guys can play with this link with yourself here. Okay, and let's then implement one example of this by hand. Let me find this spreadsheet. I think it's this one, CNN binary. Okay. So first, I want to show the kernel operation in how it would be in a spreadsheet. So for example, I will create a kernel here for edge detection. This kernel here is specialized in the left edge, the right edge. How can I apply this kernel to this input image? So first, I have to basically multiply this kernel to this image. So this is a element-wise multiplication, and then I have to sum those values. And since this is a multiplication operation, I have to use Command Shift Enter here to perform this operation. And then I want to repeat this operation. Okay, here I have number 2, and then I want to repeat this operation to those other values. So what I'm going to do here is to fix this matrix so that I can copy to the other values. And okay, so this kernel became specialized in actually the right edge of this image. So I have greater values here and lower values here. If I use the same as an example from the class, -4, for example, then I have a edge detection. Actually, those values are inverted, but still. Okay, but let's visualize this in a real image. So maybe it's better to see this in a real image. How this would happen in this image. So I have here the MNIST data set. My true data is here. So each row of this data set is 1 digit. And here in this first column, I have the true value. So for example, here I have the number 4 in the row number 13. And those are the pixel values. So if I go here and put the row number 13 from data, then I can see here the number 5. And I am going to demonstrate here how would be this first operation of weights and applying value. So as I mentioned, the weights, those values of weights, they are initialized randomly. So at first, they are random. So I'm putting a weather here, like also like random values between -5 and 5, for example, just to give an illustration of what would happen in a real case. So those values are random, and then here we'll have our first feature map, which is going to map those weights into this image. So it's basically the same operation that I performed before. So first I'm going to multiply this matrix to the first block here. Then I'm going to fix here those values. I'm going to sum them. And here I want to apply the ReLU activation function. So if you remember from the previous webinar, the ReLU is a very simple activation function. You're basically canceling any negative values and getting only the positive values. This can be implemented here as the maximum value between this value and 0. And then let me confirm here. So what's this value? So for example, suppose that I have here one value. Let me put here -4. So if I have this operation max of that value and 0, so if I have a positive value, then the value will return the very same value. If I have a negative value, then the value is going to return 0. So this is what's going to happen here. And then I can apply the same operation to all the other pixels. So now here I have a feature map of those weights being applied into this image, and then here I have what was mapped. So as I mentioned, initially those weights are random, but after a while they can become more specialized in some specific feature. So for example, let's suppose that this weight matrix became specialized in finding the bottom edge. So I'm going to implement here how would be a convolutional matrix for this case. And here I have a feature matrix that is identifying so the top of this image. So let me change here to a different image. For example, this row number 2. So it's always identifying the top, like the top edges. Or if I implement this, the edge detection, which are those values, -1, and here 4, 0, and -1. Oops. And now here I have a edge detection. And then this process, and then after this, I have the max pooling, which is also a very simple operation. I simply have to get the maximum value from each 2x2 squares, for example, in this case. This is a hyperparameter that you can input. So I'll get the maximum value. It's just a max operation. And then I repeat this same operation for all of those other pixels. So I reduced this the dimension of this image. Instead of 14 by 14, now I have a 7 by 7. And then the same process is repeated again. Weights and value, max pool, and then flattening. I have here an ready implementation of this. So I have here max pooling, then weights, then value, which is the same of here, max pooling. And then after you have a reduced image, then you can flatten it. So the flattening process is basically getting each of one of those values and converting into a 1D array. And then the rest of the process is a fully connected network. I have one weight associated to each one of those values, which give the importance. This is the bias here. And then I can apply, for example, here an activation function here. In this case, the sigmoid is not the best activation function because it's for a binary output. So it would be useful only if I want to predict either if it's a 1 or 0 in the input. But still, it's good for illustration. And all right, so this is how I would implement the MNIST and visualize in spreadsheets. And finally, one last thing that I want to show you guys, it's quite important, but I didn't mention before, is how are those convolutional images applied to colorful images. So I have here the very same image of a car, the colorful car, but when you have a colorful image, what you actually have are different channels of the image. So here I converted, I used a website to convert the images to spreadsheet. Those websites exist. It's a very interesting website. So it basically converts, and what I did there, I converted that image of the car to a spreadsheet. So here, what I have as input in, if my image is colorful, is actually the different channels of this image. Because when you combine those channels, then you end up having a colorful image. Let me show you how this happens. I have here hidden a and hide here. So basically, a colorful image is actually an image that has all the three channels combined with each other. So if you select this, we can't see so much meaning in the image. But if you give a zoom out in the image, you end up seeing like those colors being combined. So that's how a colorful image is created. And since now here I have three channels, how is this convolutional operation applied to this image? So the convolution is actually applied separately to each one of those channels. I have here one example with this applied. So basically, I have one kernel that it's only for the red channel, one kernel that it's only for the green channel, and one kernel that is only for the blue channel. So when you have colorful images, you are actually always will have the sets of three kernels. So for example, here I have one edge detection applied to the red channel, and if now I put all other channels combined with each other, so here it's the output. I have here one input as the original image, and here as output I have like the combination with each one of those kernels. So in this case, I choosing values here for edge detection. So actually, when you are dealing with colorful images, what you have to know is just the fact that instead of being applying one kernel to the input image, you will be actually applying three kernels, each one for one of those channels in the image. And this would be the case of a RGB image, which is the case here, red, green, and blue. Okay, so that's what I planned for this webinar. I hope those spreadsheets were useful for giving a more intuitive view of what's going on inside, what operations are being applied to the to the images in a convolutional neural network. And yeah, for now, that's all. And thank you for watching, and see you guys in the next webinar.